Right. So good evening again. Um, we open up this thing. Oh, open. Where's this thing going? Right. Um, so let me know if you can't see the presentation or the pointer or anything. So today we deep in section 5, which is security fundamentals. So I know a lot of you very passionate about the security stuff. Um, so we'll be touching on certain things here. Most of it is basic descriptions of stuff. The other security courses that Shiva will offer will have a lot more white hack stuff and white hack hackers and all these Kali Linux tools that you'll get into. But from the Cisco side, they just wanted to understand the fundamentals. So that's what we're going to be covering. So we'll go through some access control, password policies, VPNs, and then Tuesday we'll go into the ACLs and some layer 2 security features. So first, let's get into a brief recap of last class. So we started off last class with this thing called QoS, or quality of service, QoS, right? So in our last class, we discussed quality of service, or QoS, and how we can classify or differentiate our traffic flows into different service classes. We discussed key metrics such as bandwidth, delay, jitter, and packet loss, and how different types of applications depend on these metrics in different ways. So we basically say we have applications that we know. We have WhatsApp, we have Facebook, online gaming, your Call of Duty and your FIFA and those kind of things. You have Skype, like what we're using now, web browsers, what else? All the different web applications that you use. So all of these things have, or all of these applications have certain characteristics that you could use to classify or differentiate your traffic flows. So a flow is just a path between you and a server, right? So if you're using WhatsApp, you probably have a flow between you and a WhatsApp server, and a flow between you and somebody else that you're WhatsApping. So a flow is just a flow of packets, basically. And then each of these applications, after we classify them, we could look at their behavior and we could realize that different metrics apply to different applications differently. So for instance, if you stream in a video and you want to watch a nice 4K 60 FPS video, bandwidth is most likely going to be your biggest constraint there. You just need to push a lot of packets through your pipe. Whereas if you're doing like a Skype call, like right now, delay, jitter, and packet loss will be a lot more important than pure bandwidth. If I pull up well, I don't have any apps installed right now, but if I pull up a real-time bandwidth monitor, you'll see that I probably using 2 or 3 megs right now. But if you vary the delay, jitter, and packet loss, well, significantly, you realize that you see no hand moving, but you don't hear my voice, or you're seeing pixelation on your screen, or you can't see my screen properly, or you're just missing half the screen because half those packets being lost. So some different metrics apply to different applications. And we also illustrated how routers use different buffers to queue or store packets for the different classes. So we have buffers, which are just small pieces of memory on a pieces of hardware. Everything has buffers, basically. Your phone, switches, routers, computers, everything. In routers especially, we use these buffers to queue or store packets temporarily for these different classes. We discussed how we could implement different policies to tell the router, hey, this queue or this buffer has the highest priority. As soon as you see a packet stored there, just pull it out one time. Because those are our gold level customers, or that's very important application traffic for Skype or for WhatsApp. Whereas this other queue could have video traffic. So don't worry to pull that out quickly whenever you could get around it. You also mentioned different fields that can be used for marking packets for quality of service rules. So we went in and discussed things like the DSCP, which I said was just a special header field that you could set yourself to tell all the other routers, hey, I analyzed this traffic and I classified it as a certain type of traffic. Maybe I classified it as streaming traffic. And to make sure that you don't have to go and do that analysis again, because that's a very time-consuming process, I want to mark this packet and maybe I want to color it with red. Or in terms of DSCP, maybe I'm going to put the SCP code 0x67, which will be WhatsApp traffic, and which only our routers will know is WhatsApp traffic, just so that they don't have to go and redo this entire thing. Then lastly, we discussed the differences between policing and shaping, and the impact that these two methods can have on different types of traffic. So we said shaping was storing the packets, whereas policing is dropping the packets, right? So if you configure a customer for, let me say, 10 megs per second, and they're trying to push 20 megs per second, are you going to just drop all the extra packets after 10 megs a second? You're just going to discard everything else? Or are you going to try to store some of those packets and then burst all the packets after? So maybe there's a spike to 20 megs, and afterwards it drops back down to 0. So are you going to try to store those packets and then kind of level it off so that that 10 megs could be a little more consistent? Or are you going to see when they cross the 10 megs, just drop off everything else, so that even if it drops back down, those packets are already lost? We don't care. And these methods could have different behavior on different types of applications. So different ones may be suitable for different applications. Then we went through configuring network devices for SSH access. So we then proceeded to discuss the configuration of Cisco devices for SSH access. We began with some background info on the weaknesses of the Telnet protocol. So we basically said, don't use Telnet because anybody can sniff your traffic and figure out your username and password. We then configured some local user accounts. We set the host name and the domain name of the device. We generated the cryptographic keys, and we finally configured the virtual terminal lines, or VTY, to only allow SSH access. So all of these things are commands that we enter into the Cisco device. So the commands are listed in the last presentation in case you forget. So we then moved on to some other widely used protocols in the network, namely FTP and TFTP. We discussed how we can utilize these file transfer protocols for a variety of uses, including transferring iOS images to our devices for software upgrades, storing backups of configuration files for later reference, storing backups of logs from devices, and whatever else we need to transfer. So these are the most common examples that I've seen. And we could use either FTP or TFTP depending on our uses. If we just want something quick and dirty, TFTP is really quick just to set up and start moving your files instantly. If it's secure configs and you want to make sure no unauthorized people have access to it, you probably want to go through the hassle of doing FTP with proper usernames and passwords, because they have that confidential information there. We then moved on to discuss security in our network, which has now become a concept that every network engineer must be familiar with. So we defined the following basic concepts. Vulnerability is anything that can be considered a weakness in a system. An exploit is a tool or method developed to take advantage of these vulnerabilities in a system. A threat is the possibility or danger that an attacker could leverage an exploit to take advantage of a vulnerability in a system. And then mitigation techniques, which are the methods or safeguards that we can take to prevent malicious activity directed at the systems. So you see, it starts off with the vulnerability, which we have in a lot of systems, and then it develops from there. Somebody might develop an exploit to take advantage of that vulnerability. Then a threat will exist on our side when we know that an attacker could leverage that exploit to take advantage of that vulnerability. And then we need to put in some kind of mitigation technique to prevent that malicious activity, or to prevent the possibility that somebody could use an exploit on our systems, on our vulnerable systems. So it just builds up from here, going up. Then lastly, we discussed some key elements that the security program of any enterprise must include, namely, improving staff user awareness through constant reminders, notices, bulletins, manuals, training sessions, whatever it is. We always need to strive to improve our staff user awareness. We host training sessions with key staff members to continually improve and reinforce their security practices. And then we install and maintain physical access control systems to physically protect our network nodes, right? We don't want people just being able to pick up our router and go with it. It's a multi-million-dollar piece of equipment. So we need this physical access control as well as this user awareness and training. So now let's move on to some new material to continue this discussion on security fundamentals. We have already mentioned the concept of AAA services, explaining how TACACS Plus and radio servers can be used for remote device authentication. However, there are many cases where local passwords need to be configured on Cisco devices as well. If we attempt to use these local passwords to secure our Cisco devices, we need to be sure that we understand how to do so safely. One of the earliest ways to use passwords on Cisco devices was to configure the particular line, so either the console line or the VTY line, using the password X and login commands. These commands are configured after or under the line con0 or line VTY 015 commands. So you'd have done this sometime in your lab, either do config T and then line console 0 or config T and then line VTY 015. And then under these, you could put in these two commands now. You could put in password something and then login. So you see password Cisco and then login. So this means that when you put your console cable in, so this Cisco device, this switch, is going to check for that password of Cisco. So you could either put login or login local here. If you put login alone, it just checks the password. So you see we only put in the password, so you put login. So you're only going to have to put in a password there, not a username. This configuration does accomplish the goal of password protecting our device, but the password is clearly written in plain text in our configuration. A slightly more secure way to perform this configuration would be to also enter the service password encryption command, which encrypts the password with a weak encryption algorithm. So you see, you just go config T here and then put in service password encryption. So this service password encryption command doesn't just apply to this password here. It applies to all plaintext passwords in your Cisco configuration file, and it will basically try to hide it or encrypt it with an algorithm. Now, it is good, and to you, you might watch this and say, well, this is clearly much harder to decipher than Cisco. But actually, no. So there are websites, and let me get this right. There are websites like this. There are a ton of them. I just pick one here that clearly have a Cisco password cracker just easily available here. So you'll see I put in the same thing here. Here, password 7, and then this thing here. So the 7 is just describing the encryption algorithm. This is the real password here that it's encrypted. So I just put that there, click crack password, and you'll see it come up with Cisco. It knows how to decrypt that password and get Cisco back. And people could do that from your configuration file very easily. So you'll see this is not safe at all. A bit safer than just putting Cisco there. But there are tools easily available to crack that password with the service password encryption command. So don't rely on this too much. Unfortunately, this encryption can be easily decrypted using online tools. A much more secure way to use local passwords on Cisco devices is to use the secret keyword. Using this keyword forces the device to hash the password that you enter, ensuring that the password is much more difficult to decipher. One example of using the secret keyword is in protecting the escalation from user exec mode to user privilege mode using the enable secret password command. So you could put the same Cisco here, but you put enable secrets and then Cisco. So it encrypts that Cisco password with a much more robust algorithm. So that's the difference between enable password and enable secret. You'll hear people, or you might see people say, if you want to encrypt this user privilege mode, just put enable password and put the enable password. But now you know that you should not put enable password. So you put enable secret and put your same password there. No difference. But the difference here is, you see this 5, which is different from you have secret 5 now. So you see that's different from the 7 that we were seeing before. And you see this long string here, which is very different than what we had before. If we go back to that same online cracker tool and we put this entire thing there, it won't be able to decipher this into thread. So since the enable keyword using MD5 hashing by default, you can rest assured that your passwords are much more difficult to decipher if someone obtains access to your configuration file. This stronger security can also be extended to your console and VTY lines by using the username something and then secret something command instead of the password something command. So you could put either, in the same way you could just put enable password instead of enable secret, you could put username and then password. So instead of that password, we are now saying you should use secrets. So like username Rishi, secret Rishi, or secret Cisco, whatever it is. So we're replacing this password command here with secret. And we use this to create local accounts. And then we use the login local command under our lines. So if we just put a password, we put the login command. If we put both a username and a password or a secret, we can use the login local command. Once we configure this, we will be prompted for both a username and a password for logins, which adds accountability to our logins as well. So accountability just means figuring out who changed what or who logged in when. So we have a username to put to the command. So instead of just saying, somebody logged in with the correct password, now we know Rishi logged in or anything else, Shiva logged in, whatever. We have a username to put to that login. So we know if something breaks, it was most likely them. So these are the full commands here. So we go enable and then config T, and then username Rishi, secret Rishi, or username student, secret password phrase Cisco, whatever it is. So instead of putting the password command here, so after I put username Rishi, if I had put a question mark here, I would have seen I could put either secret or I could put password. So we're saying now use the secret because it's much better encrypted. Then after we configure the local usernames and secrets, we go line VTY 015, and then we put login local. And this will this will force your router to let people use both a username and a password when they're logging in. And you see when you do your show config, you see, you show run, you see username and then the secret, and then you have a very long string here, which is very difficult to decipher. So now that we know how to configure local passwords for our devices, let's discuss how we can formulate policies for the creation of secure passwords. So we're not talking about, this kind of secure passwords now, right? We know how to do secure passwords on a Cisco device. We're talking about in general now. What do we do to get secure passwords in life? So for many persons, passwords are an unnecessary burden to remember. And as such, they choose a simple password that they reuse on all of their accounts. When certain sites started pushing these users to use different passwords, some of them started writing these passwords down in a notebook so that they wouldn't forget them. So I'm sure a lot of you guilty of this, right? Either you have, some password that you think you alone use. So for instance, password 123, or green tree 321, whatever it is, you use that password for your Facebook and your WhatsApp and whatever else that requires passwords. And because you know that password, you try to reuse it as much as you can. Or if you're being forced to use different passwords, or if you want to use different passwords, you start writing down your passwords in a notebook, right? And a lot of people feel that these are secure. So that's why Cisco tried to push this topic so that we could learn better. So password management refers to procedures that users follow in generating, storing, and retrieving their passwords. There exists a number of good free password manager applications online that aid you greatly in this process. So don't feel like you need to sit down and become an expert in password policies or an expert in hacking to have secure passwords. There are a ton of useful apps or add-ons on browsers that are called password managers. So this is an example of the one that I use, right? It's called LastPass. I have no affiliation and I do endorse them in any way. Pick one. Google Password Manager, and a bunch of them will come up. Just pick one that well reviewed and seems to be nice. And this is the advantage that it offers, right? So it generates a password for you. It will never use the same password twice in two different applications. So you click this little button here, and it will show you, this is the password I want to use there. And it looks crazy, right? You will never be able to type this or remember this. But what it does is that when you click fill password here, it stores it. So that whenever you come back to this application, you will see a little button here saying auto fill password, and you could press yes, and it will automatically pull back up this password and fill it for you. You don't need to remember this. You could also select different configuration options here. You could put your password to however many characters you want. You can make it easy to say and easy to read. Select all the different options that you want here. Maybe you only want a lowercase password because your website or or your app doesn't require all of these things. So you could put these different options here and just press fill password, and it will generate a super secure password for you, and it will make sure that this is never reused, and it's secured in a very secure database. So using these password managers, you can ensure that your password complexity meets the requirements set out by your enterprise or application. Common password complexity requirements involve generating passwords with a particular minimum length and including a minimum amount of symbols and capital letter variations. So I'm sure you would have seen, if you try to type in password 123 in Facebook or in Gmail or something, they would have said password needs to be longer than 20 characters, or password needs to have a capital letter, some kind of weird symbol, at least 2 variations of some things, a few numbers, whatever it is. And these password manager applications can help a lot with that, right? And a lot of these apps know that you want to include this in your password, so they will have those options. Now, certain applications also push the use of passphrases, which are just long strings of words over complex passwords, as these passphrases are easier to remember. So I always push this in whatever enterprises I can. Whenever I'm creating passwords, I try to push passphrases over passwords. The research is there, and I'm not a security expert by any means, but the general idea is that you have these things called ASICs or GPUs that could just crack through passwords really quickly. So if they were trying to guess, password 123, for example, they would start off with the first letter. They would say A, B, C, D, E, F, G, and they would just keep going like that. And then they could just iterate over that first letter, and the second letter, and then the third letter, and keep going through like that. And because these things so fast, they could brute force passwords or guess these passwords very quickly in a few hours most of the time. And there are lots of graphs and charts and stuff. Shiva will discuss it way more in his classes. But the idea is that passphrases are really long, so these GPUs and ASICs can't guess them very easily because they are long strings of words. But they're also easy for us to remember. You can imagine how difficult it would be for us to remember something like this, right? But if you look at it, it's only 12 characters. So theoretically, a GPU or a ASIC could guess this if they were tailored to guess, something with an exclamation mark and an asterisk and all of these things. If you instead use the passphrase, like, let me see, all banana trees have monkeys. That's a very long password. You could remember it because it's funny and it's something that you might say. And it's very difficult to program a GPU or ASIC to guess something like that, because how many variations of that are there? Somebody might say, all boats have blue sails, and then somebody else might think up a word in something, a different language, or they might rotate the word so that it doesn't actually make sense forwards, but it makes sense backwards. And it's super long, so you can't put in all the possible words into this brute force attack. So you'll see a lot of security folks try to push passphrases over complex passwords because of that primary thing. It's easier for humans to remember. So lastly, the use of multi-factor authentication can also greatly increase the security of our devices. Multi-factor authentication aims to draw authentication from a number of different areas in order to validate a user login. Some of the main areas are something you know, which is a username and a password and a PIN. What else? You have a lot of things that you need to remember. So we are accustomed to these something you know, but we have more recently tried to push these other two. So something you have, which is a key card or a key or a chip or a certificate or a mobile phone, for example, and then something you are, which is a fingerprint or a retina scan. What else we have? We have the fingerprint readers in phones. We have facial scans in iPhones, I believe. The something you have, you'll see a lot of things try to use your phone for this now, because we always have our phones. So they'll tell you, enter your username and your password, and then check your phone and press yes on your phone. So that's something you know and something you have. And then on your phone, you might have something you know and something you are. So you'll have a PIN on your phone, and you'll also have a fingerprint reader or a facial scan. So a lot of apps try to use things from at least two of these fields. So in order to qualify as multi-factor authentication, you need to be using at least one from more than one field. So if you use username and password and PIN, you're still not multi-factor authentication, because that's the same factor here, is in one group. If you use username and keycard, then fine. If you use username and keycard and fingerprint, great. You have 3-factor groups there. So these are some of the examples. You see you have your fingerprint reader here. You could do a hand signature. You could do a heartbeat rate monitor. The stuff we enter on the keyboard as normal. A tooth implant in some way, I guess, for very high-tech places. Your facial features or your facial heat map. The back of your eye, the front of your eye, your specific posture or your manner of walking, the layout of your hand. Some of these weird, but people can use them. The specific shape of your ear. So people think up all sorts of weird things because hackers are always looking for ways to get around this, right? So we know we could forge signatures. You've seen the movies of people either take imprints of thumbs with wax or something, and then they reuse them. You'll see a lot of these weird, but they're also way more difficult to crack, which is why researchers will always be looking at these things. So traditional security methods attempted to stack multiple factors from the something you know field, but modern methods are attempting to mix factors from different fields. For example, biometrics are typically tied to a single person, and distinctive factors such as fingerprints and retina scans can be used to authenticate users. Digital certificates are files that are generated and signed by a trusted entity called a CA or certificate authority. These certificates include important information to identify and validate the user, such as the entity that they were assigned to, their CA, their expiry date, and the rest of the user's combined public and private keys. These certificates can thus be used to further strengthen security. So we may not think of it as much because it just kind of works in the background, but all of the HTTPS sites that we visit have these things called digital certificates. So how it works in a nutshell is that we have these bodies, these organizations, I guess, called CAs or certificate authorities. So their job is to validate hosts and say, hey, this is a valid Google server. If anybody is coming to visit this server, check this certificate, and I have given my seal of approval to this server so that you could check the certificate and say, hey, this is a valid certificate. This is a valid Google server. Whereas if somebody else were to deploy a server and claim to be a Google server, the CA might check and say, hey, this IP address weird, or this domain name weird, or this user weird, or this time zone, or something off with this. I'm going to reject your certificate or reject your certificate signing request, and you're not going to have a valid Google certificate. So these CAs really work to validate these servers. And anyway, anytime you see the green lock next to your URL in the left-hand corner there, it means that there is a certificate associated with this site. So you can feel free to click that green lock, and you'll see a certificate just listed there, validated as somebody or authorized as somebody, and you'll likely match that to the domain name that you go into. So if you go to Google, you might see validated as Google Inc. And that assures you that a CA has vetted that server or that URL or that machine in some way and said you are in the correct site. And we also use digital certificates in other things, not just servers. So you could use a certificate to log into a router, for example. Instead of always supplying your username and password, you could assign public and private certificates to your router, and then take a certificate and just present that to the router and say, hey, I had a certificate that I created a while ago, and you were instructed to trust this certificate, so look it here. Instead of saying, hey, look my username and password, you say, hey, look my certificate. And because the router knows that this was generated and signed by a trusted entity, the router will say, no scene, I accept your login. So this is just an example of what I'm talking about here. So this is some random certificate on some server. You'll see issued to there, issued by, so you see CA here. This is the CA that issued this certificate. This is how long it is valid for. So if you go on, the 17th of May in 2014, this certificate will be expired, and you'll see a warning coming up saying this certificate is expired. And this is who it was issued for, healthcare.gov. So now that we understand a bit more about passwords in our network, let's move on to another important concept, VPNs. To understand the overarching idea behind VPNs, first think of an isolated private LAN in a single enterprise office. So this is what we had, right? This is what we know for a whole course in CCNA. This is what we were building up. We have printers and laptops and servers and stuff. We have some access level switches here. We connect to some bigger distribution layer switches, and then maybe some core switches or routers. And we create our enterprise LAN or private network inside our enterprise like this, by just linking up a bunch of switches, basically. Users within this LAN have all the access that they require. They can access other host machines within the LAN, as well as servers or printers. However, we of course have one large limitation. LANs are limited to a particular small geographical area. So for example, this might be one small office, and this might be another small office in the same building, usually. This means that as soon as we leave this area, we lose access to all of these LAN resources. On the other hand, we now have access to a large, almost ubiquitous network across the world, the internet. Can we somehow use this internet to connect into our LAN remotely and access resources as if we were in that geographical area? This is exactly what VPNs aim to do. So, especially now, a lot of us will know of this concept, right? The whole work from home thing. So before, these resources may have been isolated, and they might have said, you could only access your SharePoint drive or your work storage when you're in the office. If you're outside, then hard luck, you can never get to this. But now, or for any organization that has digitized and moved to the work from home and all of these things, they've said that we want people to be able to access these resources from anywhere, using this big thing called the internet that we don't really trust. We want to be able to secure users and give trusted users access to this very important resource, or these very important resources in our network. The trick here is that this server might contain something, let me say in digital, right? We make a lot of money by offering very innovative mobile plans. So we might have a new mobile plan that we know people are going to be excited about. Let me say we know users very interested in this new app called TikTok, and they want TikTok access. So we say we're going to bring out a bunch of new plans and get people excited based on this new app, because we know that they're excited about this app already. And we have a ton of presentations and technical details and everything stored in this file server about how we're going to roll out that. Now we want to be able to allow people to be able to access these very secure files, right? Because they need to create it and get this project moving. But we want to make sure that while we're doing that, no one from TSTT or anyone else around the world actually could get access to that file. It needs to be limited to the people inside the company. So that's exactly what VPNs aim to do. VPNs can be broadly categorized into two groups: remote access VPNs and site-to-site VPNs. Let's explore remote access VPNs first. So remote access VPNs aim to allow remote users, such as employees working abroad or on the field or home, to connect to their enterprise's private LAN over the public internet. These VPNs can be implemented in a variety of ways, using special client software from a number of vendors. Usually these are firewall vendors. So one such VPN client is the Cisco AnyConnect Secure Mobility Client software. So of course, this is a Cisco course, so I have to give a Cisco example, right? But there are a ton of different client softwares you could use. So this client uses Transport Layer Security, or TLS, to create the VPN remote access tunnel, so that all traffic sent over the internet can be encrypted. And that's what we want, right? We want to make sure these super secret TikTok files are encrypted over the internet, and nobody could sniff and figure out what we're doing before we launch the app. So this is what it looks like. We have our desktops or our laptops at home, and we have this Cisco firewall, or whatever other brand we use, and then we have these private servers behind here. So this firewall will serve as the endpoint for our tunnel. So we'll have TSTT or Digicel or Flow, or whatever ISP we have at home, and they will give us a basic internet access package here. And then we use this special Cisco AnyConnect client to set up this TLS tunnel to that firewall. And then between the PC here and the firewall here, the PCs will be able to set up this HTTPS tunnel. So basically the PC will be able to talk over a secure tunnel. So over this secure TLS VPN tunnel, they will be able to transmit traffic through this firewall and go to the server. So for example, if this PC was connected with this same TLS tunnel to the firewall, this PC could set up this HTTPS session or flow to the server here over this TLS tunnel. So as the diagram illustrates, these remote access VPN sessions are usually terminated on firewall devices with public IPs on the server side, so that they can be accessed over the internet. Note that these terminating devices can also be servers, routers, or other devices. So it doesn't have to be a firewall appliance in any way. You could do it with a variety of applications, but usually is a firewall. Usually the reason for that is that the firewalls usually come with a bunch of ASICs for exactly this, right? Your firewall appliance is built usually to terminate 1,000 or 1,000,000 tunneling connections, and it can do this very quickly, whereas a server or a router might not be able to handle more than a few tunnels. Usually these terminating devices prompt the VPN clients for credentials. Once the users are authenticated, they can then access resources within this LAN as if they were physically present in the office. So that's the whole point of this, right? This guy or this girl who working from home needs to be able to access their super secret stuff in this server or in these servers here. But all they have access to is this internet connection here from their home or from Starbucks or something else. So VPN and more specifically, these VPN clients allow them to set up tunnels to this firewall and access all of these resources internally using private IPs on both sides. So this is what our remote access VPN looks like in actuality. It's the next diagram just like that one. So you have the internet here, which is the biggest network we know. And then you have people who could connect to the internet in different ways. Remote workers, home users. And then through this remote access VPN, they could all set up tunnels to this firewall. And the firewall is connected to the office network. So they could access their intranet or their file servers or whatever else they have in the office over the internet through this secure VPN. However, this VPN architecture only allows to connect one or a few remote clients into our LAN. What if we wanted to connect in an entire remote office? One method would be to use a WAN circuit, as we discussed before. However, these WAN circuits are often extremely costly, especially if our remote office is on an entire separate continent. What if we could tweak our VPN architecture to support this connectivity? As it turns out, we can. This is exactly what site-to-site VPNs were designed to do. These VPNs utilize some form of tunneling, and usually encryption, to allow a private network or LAN to stretch between multiple offices over the internet. The tunneling is used to encapsulate the private IP addresses of the LAN into public IPs. The encryption is used to protect this tunnel traffic from prying eyes on the internet, since we likely have sensitive data being exchanged over this VPN as well. So this is what we're talking about here, right? We have a branch office. Maybe this branch office is in Chaguaramas, and this enterprise central site is, in Freeport. And all we have is the internet between them, because setting up a WAN circuit from this router to this firewall here was going to cost us, I don't know, $1 million a year, because these things are super expensive. So all we do is we set up a normal internet connection on this side and a normal internet connection on this side, and we set up this site-to-site VPN here. And once this VPN is up and running, we could do something like this. So we have our PC with a private IP address here. So once you see this 10.something.something, we know it's private addresses on both sides. So we have our source address here, which is our source address here, and then our destination address here. So we want to reach a private IP address on the next side with this VPN, a router here going to drop this, right? Because you're not allowed to use private addresses on the internet. But with this VPN connection now, we using these two public addresses here, and we tunneling this traffic over it. So anything in the middle here is not going to see these private addresses. So you see here, this new IP header, that's what anything in the middle here is going to see. It's going to see this public IP address and this public IP address. And it's going to say, okay, no, see, you have public IP addresses, you're allowed to be on the internet, fine. But once it reaches here again, and this header is stripped off, then we see these private IP addresses again. And then this server, well, this switch on this server could understand this traffic from this PC, because we have the private addresses here. So the whole point of this whole thing was to allow this PC here to communicate with this server here using private IP addresses, which would have not been possible over the internet because it's private IP addresses. But with this VPN connection now, we have the encrypted payload and then the VPN header, and we have this encapsulation thing, which is basically taking this packet here and stuffing it in a bigger packet with public IP addresses here. And with this public IP address, we could get across the internet, and then once we reach on this side, we pull out this header again, and we get the IP packets inside here, and then we could get that to the server, and then when the server sends it back, it comes here, and we stuff that inside our next, think of it as an envelope. We stuff it inside another envelope, and we just reverse the IP addresses here, and we get across the internet using this outer header. Now we pull it off the envelope, and we put it back out here. So this site-to-site VPN allows us to connect this private network here to this private network here, and this opens up a ton of possibilities. So this is what it looks like in the tunneling sense. So we have PCs on this side, we have PCs on this side, and this is 192.168 and 192.168. So we know it's two private networks, and then we come here and we have two Cisco routers that have public IP addresses. So they have public IP addresses, they could communicate on the internet, no problem. So what we do is we set up an IPsec tunnel, which is a sort of site-to-site VPN tunnel, and then we encapsulate that traffic, send it across the tunnel, and then decapsulate the traffic and bring it on this side. Just like we did before. We just stop the traffic into a bigger packet with another header with this public IP address, get it over the internet cloud, get it to this side, then pull it out the envelope and put it back here. So that's decapsulation. Encapsulation, decapsulation. So notice that because of the site-to-site VPN tunnel, two hosts using private IPv4 addresses can communicate with each other. Without this tunnel, this communication would not be possible, as private addresses cannot be used on the internet. A variety of tunneling protocols can be used for this purpose, but GRE is a popular choice with IPsec used for encapsulation. So these are just two specific protocols, right? They have RFCs and everything with them, but basically they are the actual implementation for VPNs. So they are the protocols we use to implement these VPN tunnels. One major difference to note with site-to-site VPNs is that they are usually always on, whereas remote access VPNs are only used or only switched on when end users are ready to connect. So usually with something like this, we will just leave this tunnel up and running. So anytime you want to get from here to here, you just go through this tunnel and no scene. With your remote access VPN, you usually only connect that when you need to get into the office network. So these site-to-site VPNs can also be used in multiple locations, making a variety of architectures possible. So we could have, Chaguaramas, the ABA, Point Fortin, Freeport, and we could set up site-to-site VPNs with all of these going over the internet. So you see here, any internet access technology. So we could have this router here and get a normal flow link. We could have this here and get a normal TSTT link. And then we could have this here and a normal digital link. And using this basic internet connection, we just set up our IPsec or our GRE tunnel between these two routers here. And then we could tunnel our traffic over this, whatever is the underlying network, we don't care. We just tunnel in over this tunnel and getting it between these two routers, just as if we had a WAN circuit between them. Yeah, just as if we had a normal link between them, even though this traffic might be physically connected to something in very different ISPs, in very different data centers, we don't care. Somehow the traffic will get to this side, and for all intents and purposes on our side, this is basically a link between these two routers. And that's it for today. So we're gonna continue the rest of it Tuesday. So yeah, we have ACLs and then layer 2 security features. Yeah. Any questions about anything from today? Okay, cool. No questions yet. Right, so I'm gonna stop the recording.